James Webb Telescope gave us a stunning first look at the depths of our universe.
In July, a single image captured by the James Webb Space Telescope triggered a wave of awe, confusion, and speculation across the scientific world. At the center of it all was WR-140, a star system that, until then, was mostly known to a small circle of astronomers. But now it was making headlines. The photo revealed something no one expected. A series of ripple-like rings encircling the star, clean and structured, stretching out into the void like cosmic fingerprints. And they weren't just rings, they were geometric. Some appeared square-edged, like the folds of origami drifting in space. Even for seasoned professionals, this wasn't normal. The image gained viral momentum when citizen scientist Judy Schmidt shared it on Twitter. Her interpretation of Webb's raw data sparked millions of views. At first glance, it was beautiful. But the longer people stared, the stranger it felt. Conspiracy forums, space journalists, and amateur astronomers latched on. Was this a message? A structure? Something built rather than born? While NASA remained cautious, public curiosity exploded. A few scientists compared the structure to Dyson spheres, theoretical megastructures built by intelligent civilizations to harvest energy from stars. Others proposed it might be a massive beacon, perhaps an alien artifact reflecting light in perfect pulses. Even among experts, confusion reigned. This wasn't what they had expected from a dying star. It looked too clean, too deliberate, too impossible. But as the internet buzzed and theories bloomed, astronomers began digging deeper into the star behind the spectacle. Because to understand the image, one had to understand WR-140. And the truth of what created those ripples was hiding in the fury of its heart. What is WR-140 and why it matters? WR-140 isn't your average star. It's one of the galaxy's most volatile celestial beasts, a Wolf-Rayet. These stars represent the final burning stages of massive stellar life. They're hot, unstable, and shedding mass at an astonishing rate. WR-140, in particular, is in a gravitational dance with a massive blue supergiant companion, and their orbit is anything but gentle. Every 8 years, the two stars come dangerously close. Their immense winds, blasting outward at thousands of kilometers per second, collide like dueling hurricanes. The energy released in these encounters is staggering, and for reasons scientists have long studied, it's during these near misses that WR-140 begins to shed carbon-rich dust into space. But WR-140 is rare even among rare stars. Most Wolf-Rayet systems are hidden behind thick clouds of galactic dust or burned too briefly to be observed in detail. WR-140 is not only relatively nearby, but it's also uniquely well-positioned for Earth-based and space telescopes to observe its activity without interference. The system's outbursts, when they occur, act like cosmic timestamps. With each close pass, a new layer of dust is flung outward and carried into space. Over decades, this process creates concentric shells, almost like the growth rings of a tree. But in WR-140's case, they're rings of light and matter, drifting outward at nearly 1% the speed of light. That alone would make WR-140 a stellar gem for astronomers. But with JWST's unmatched infrared capabilities, what was once theory suddenly became visible. And as the scientific community focused its lens more closely, what looked like alien design began to reveal a deeper truth, a breathtaking dance of physics, orbit, and time. Wolf-Rayet stars, monsters of the cosmos. Wolf-Rayet stars are the universe's true titans, violent, massive, and burning with an intensity few other stars can match. They're more than 25 times the mass of our sun and can burn 10 times hotter, pouring energy and particles into space like a cosmic flamethrower. Their lifespans are tragically short by cosmic standards, mere millions of years, ending in spectacular supernovae or even direct collapse into black holes. What sets Wolf-Rayets apart is how they die. They don't go quietly. They shed their outer layers violently, casting off hydrogen and helium through powerful stellar winds moving at thousands of kilometers per second. These winds sculpt the surrounding space into bizarre shapes, bubbles, arcs, and spirals that hold the key to understanding not just how stars die, but how galaxies evolve. WR-140 stands out because it gives scientists a rare window into this process. Most Wolf-Rayets are either too far, too hidden behind dust, or too short-lived to study in detail. But WR-140 is positioned just right, with just the right companion star, and just enough transparency in its environment to give astronomers an unobstructed view of its outbursts. when the binary stars interact, especially during their closest passes. Their colliding winds trigger dust formation at massive scales. Unlike most stars, this one doesn't just burn, it builds. And what it builds has turned out to be one of the most symmetrical, mysterious structures ever caught on camera. This makes WR-140 a Rosetta Stone for stellar death. Every ripple it emits is a record of that final, furious chapter. And just as scientists began decoding those ripples, they were forced to confront an unsettling question. Could anything this perfect really be natural? Alien megastructure or optical illusion? The first time many saw the image, the reaction wasn't scientific. It was visceral. Those rings around WR-140 were too precise, too sharp. The square edges in particular defied expectations. In a universe shaped by chaos and chance, how could something so geometric form on its own? The comparisons came quickly. Dyson spheres, interstellar beacons, the architecture of an advanced species. If a civilization were to build something to harvest stellar energy, it might look like this, layered, orbitally symmetric, and expanding outward in pulses. Even mainstream scientists couldn't dismiss the visual parallels. Was this the ultimate "we're not alone" moment? The reality, however, was more grounded, though no less remarkable. Some astronomers believed the square-like appearance wasn't due to structure, but to perspective. The rings, while nearly perfect in shape, were being viewed at an angle that compressed their curves into lines. Still, the consistency of spacing, sharpness, and clarity was difficult to chalk up to randomness. Others pointed to the JWST's sensitivity and image processing techniques, which could enhance certain features, making natural dust shells appear more structured than they actually are. But even with these explanations, the image retained its strange aura, because what looked like engineered design was, in fact, the result of stellar timing and physics too elegant to have been imagined by humans. Still, the alien hypothesis refused to fully die. And in some circles, it didn't need to. Because even if the rings weren't the work of other civilizations, they might still represent something equally rare, nature's version of mathematical perfection. And so astronomers looked deeper, not for signs of life, but for signs of logic. The rings had a rhythm, the dust had a pattern. There had to be an explanation. And as they followed the trail, they discovered a mechanism hidden in the star's orbit, a cosmic engine that creates rings like clockwork. Decoding the dust shells. What looked like a static structure was actually a motion picture in space. Each ring a moment in time, a ripple frozen in the vacuum. Astronomers began to understand that these weren't true rings like Saturn's. They were expanding shells of dust, formed and flung into space by a highly specific rhythm, the orbit of WR-140 and its blue supergiant companion. Every 8 years, as the two stars swing close in their elongated elliptical orbit, their powerful stellar winds collide. At this precise moment, carbon-rich dust is forged and ejected into space. It's not a constant outflow, it's a burst, triggered only when the stars are near enough to ignite the reaction. Over time, these outbursts stack on top of each other. Because the stars return to the same point in their orbit like clockwork, each dust shell is layered evenly around the system, expanding outward at roughly 3,000 kilometers per second. As they travel, they cool, drift, and eventually catch the light, becoming visible to instruments like the James Webb Space Telescope. But the pattern isn't spherical, it's spiral. Imagine a cosmic lawn sprinkler releasing puffs of dust in perfect intervals. From Earth's angle, that spiral flattens into a series of rings. The illusion is breathtaking but entirely natural. Still, it took decades of modeling and observation to confirm it. And even now, not all questions have been answered. Why are the rings so clean? Why do they retain their sharp edges over such vast distances? As scientists pondered those questions, Webb's data revealed something no one expected, a subtle inconsistency in the speed of the dust, hinting at a force not yet fully understood. And that led to one of the most surprising discoveries of all: dust accelerating through space. Pushed not by gravity or but by light itself. How the JWST made this possible for decades. WR-140 had been studied from Earth, but something was always missing: clarity. Ground-based telescopes could detect its behavior and measure its bursts, but the surrounding dust was too faint, too cool, and too distant to reveal the full picture. That all changed with the arrival of the James Webb Space Telescope. Unlike any observatory before it, JWST was built to see the unseen. Its infrared instruments weren't blocked by dust. They cut through it, It could detect heat, trace faint signals, and render ancient, cold structures as if they were glowing in daylight. When it turned its gold-coated mirrors toward WR-140, it didn't just take a photo, it uncovered a history. The image revealed 17 full rings, each one representing a distinct outburst from the system. That meant JWST had captured over 150 years of stellar activity in a single shot. Each layer was a time capsule, an expanding memory of a close stellar past long since completed. And for the first time, astronomers could study these layers in crisp detail, like grooves on a vinyl record spinning in space. The resolution was so sharp that even the oldest, faintest shells, ones that had traveled billions of kilometers, were still visible. Their symmetry, their spacing, their direction of travel, it all told a story that no previous telescope could read. But just as scientists began to marvel at this visual timeline, they noticed something strange. The rings weren't exactly where they were supposed to be. Some were slightly ahead of predictions. Others stretched farther than models allowed. Something was influencing the dust after it had already left the star. The answer wasn't a glitch. It wasn't an error in calculations. It was something long theorized but never directly observed. The dust was moving faster than it should. It was being pushed. And the force behind it wasn't gravity, or heat. It was light. The Sydney surprise, 20 years of secrets. As stunning as JWST's image was, it didn't come out of nowhere. For over 2 decades, astronomers from the University of Sydney had been observing WR-140 using one of the most precise tools in ground-based astronomy, interferometry. By linking telescopes across vast distances, they were able to create ultra-high-resolution views of the dust spiral, though never as clear or complete as Webb's snapshot. What they built over years of observation was a 3D model of the dust's behavior. It confirmed that WR-140's spiral pattern came from its binary orbit. The interaction between the two stars, especially at close approach, was forming the dust and shaping its outflow in predictable, repeatable ways. They had mapped the rhythm. They understood the pulse. So when JWST's image arrived, it wasn't just a surprise, it was a confirmation. The geometry of the rings matched the models from Sydney's team almost perfectly. For scientists, this was an extraordinary moment. Independent verification from 2 very different systems, one in space, the other on Earth. It meant the structure wasn't a trick of the light or an image processing artifact. It was real, but even with their deep understanding, one detail didn't fit. In their simulations, the dust moved outward at a steady pace. But in JWST's image, some of the rings seemed to accelerate slightly the farther they were from the star. It was subtle but unmistakable. The models couldn't account for it. The cause wasn't in the orbit or in the wind collision. It had to be something else entirely. That's when they turned their focus to a force often ignored in cosmic dynamics: radiation pressure. A force so gentle it's hard to imagine it moving anything, yet strong enough, over time, to nudge mountains of dust across light years. What they realized next rewrote how we understand stellar motion. Dust that accelerates, a hidden force uncovered. At first, the notion seemed almost too poetic to be real. Light, invisible, and weightless, pushing matter through the cosmos. But when scientists ran the numbers, the theory held. The dust shells observed around WR-140 weren't simply expanding at a constant speed. They were gaining velocity, not from explosions or external winds, but from the starlight itself. This was more than a hypothesis. It was the first time radiation pressure had been captured in action, in real cosmic conditions. The concept had been theorized for over a century. It even served as the basis for dreams of solar sailing, spacecraft propelled by the pressure of sunlight alone. But never before had it been caught in the act, moving natural material across open space in such a vivid, structured way. In the image, the acceleration was etched into the pattern itself. The spacing between the rings subtly increased as the dust moved outward. The further the shell, the more momentum it had gathered. The light of WR-140, intense and concentrated, was acting like a wind, its photons striking dust grains and giving them a constant, gentle shove. What made this even more remarkable was how efficiently it worked. These dust shells weren't vapor. They had mass. And yet the force of starlight was enough to move them faster and faster, carving symmetrical arcs across the galaxy with precision that bordered on mathematical beauty. It was the kind of discovery that changes how we think about stellar systems. No longer just violent engines of gravity and fusion. Stars could also be sculptors, quietly shaping the space around them with the softest of touches, with radiation, with light. And in this case, that light wasn't just moving the dust, it was painting something bigger. A spiral so sharp and layered, it almost looked man-made. A cosmic sail unfurling on an endless wind. Sailing on starlight, a cosmic yacht. If gravity binds and heat burns, then radiation pressure is something subtler. A breath, a whisper, a hand guiding from a distance. In the case of WR-140, this gentle force became an artist's brush. The dust it pushed wasn't scattered randomly. It was shaped into perfect spirals, caught in the momentum of orbit and the precision of light. Like ripples in a pond or rings in a tree, each shell marked the passage of time. The metaphor quickly caught on among astronomers. WR-140 wasn't just shedding material, it was sailing. Each dust shell was like a sail, catching photons and drifting farther from its star with every passing year. The image was no longer just beautiful, it was dynamic, a moment frozen in a centuries-long journey powered by light. It gave new life to old theories about light propulsion, including the concept of interstellar solar sails. If dust could ride starlight, why not spacecraft? Why not build on this principle and launch missions across vast distances using the same mechanism that shapes cosmic rings? But beyond the technological dreams, the discovery brought something deeper, a new appreciation for the elegance of nature. For a long time, astrophysics focused on the violent, the chaotic, the explosive. But here was structure born not from destruction, but from rhythm, from repetition, from harmony. The JWST didn't just capture starlight, it captured how that light moved the universe. And as scientists zoomed in further, they realized something even stranger. The spirals weren't overlapping, they weren't breaking down. Each one was nested inside the last with a precision that defied entropy. It was like opening a set of cosmic Russian dolls. Nesting dolls in the cosmos. There's a kind of cosmic poetry in how WR-140 tells its story. Not in words, but in shells. Each ring surrounding the star system is etched into space with a consistency that borders on the miraculous. Like Russian nesting dolls, every layer fits neatly inside the one before it. No gaps, no breaks, just a pattern, perfectly preserved, expanding outward into eternity. Astronomers now believe that each ring represents a distinct chapter in WR-140's long narrative. Every 8 years, another shell is born as the two stars in the system sweep past each other. The close encounter triggers a storm of dust, which then catches the light and begins its silent outward journey. The process repeats again and again, forming a layered chronicle of celestial motion. The outermost ring is over 150 years old, still glowing faintly at the edge of visibility. The innermost ring is newborn, freshly carved by the most recent orbit. And between them lies a story of time, pressure, and propulsion, told not in explosions, but in elegance. What astonishes scientists most is the preservation. Space is messy, gravity tugs, particles collide. But here the rings remain smooth, sharp, and complete. The physics behind it, orbital timing, radiation pressure, dust composition, creates a balance rarely seen at this scale. It's not just a structure, it's a time-lapse, a living archive of a star's final movements before its inevitable death. But beyond beauty and symmetry, these rings offer data. And for astronomers, that means something more powerful than wonder. It means answers. More than just beauty, physics in motion. What WR-140 gave us wasn't just an image, it was a lab, a moving, living physics experiment suspended in the sky. Those perfect rings weren't artistic flukes. They were data-rich blueprints that revealed the inner workings of one of the most extreme environments in the cosmos. Each ripple encoded information. The distance between shells told scientists how fast the dust was traveling. The brightness and thickness of each ring hinted at the density of ejected material and the intensity of radiation pushing it. And the shape, those gentle spiral arms appearing as stacked halos, held clues about the star's elliptical orbit and how their gravitational tug-of-war choreographed each release. For astronomers, this was a rare opportunity. Usually, theories about wind collisions, orbital dynamics, and radiation pressure are tested through indirect measurements, spectral lines, Doppler shifts, heat signatures. But here was a system where you could see it all at once: geometry, timing, acceleration, decay. It was as if the cosmos had drawn a diagram in real time, just waiting to be decoded. More than that, WR-140 offered insights into the life cycle of dust itself. Dust, often overlooked, plays a vital role in star and planet formation. It's the building material for everything from moons to life, and yet watching it form, move, and evolve under such extreme forces has always been nearly impossible. Until now. Thanks to JWST, this distant star became a classroom. A way to study not just how stars die, but how they give back, shedding mass and material that will someday see the next generation of stars. The dust around WR-140 isn't just a farewell, it's a beginning. And now that we've learned to see such structures, a bigger question emerges. How many others are out there, hidden in the dark, waiting for the light to find them? The bigger picture. What else is out there? WR-140 may have captured our attention with its elegance and mystery, but in the grand scheme of the universe, it's likely not alone. Astronomers now believe that there could be countless other binary systems like it. Giant stars locked in tight, elliptical dances, shedding dust in hidden rhythms. The only reason we hadn't seen them before? We were blind. Before the James Webb Space Telescope, many of these stellar systems were cloaked in darkness, hidden behind layers of cosmic dust that conventional instruments couldn't penetrate. But now, with JWST's powerful infrared vision, the veil has been lifted. WR-140 might be the first system of its kind to be visualized this clearly, but it won't be the last. Already, researchers are combing through Webb's expanding dataset, looking for the telltale signs, subtle spirals, faint shells, echoes of massive stellar outbursts hidden in the glow of infrared. Some stars might show older, fainter rings. Others could be caught in mid-formation, still riding their first ripples into the cosmos. This discovery changes the way we approach the search for patterns in the stars. Not everything in the universe explodes chaotically. Some things whisper, pulse, repeat. Some leave behind signatures of symmetry. Messages not sent, but still received. And it begs another question. If these patterns are everywhere, could something or someone be hiding in them? The line between natural wonder and possible intention is thin. And as we stare deeper into the cosmos, it's a line we must walk carefully. The alien hypothesis isn't dead yet. When WR-140's image first went viral, it wasn't science that caught the public imagination. It was speculation. Square-like rings, perfect symmetry, geometric ripples in the vacuum of space. For many, it screamed design, intelligence, intention. And while science ultimately provided a natural explanation, one rooted in dust, orbits, and radiation, the image raised a valid and recurring question in modern astronomy. What does alien technology actually look like? If a civilization advanced far beyond our own wanted to build a structure around a star, would we even recognize it? Could it mimic a natural formation? Or worse, could it use one? Dyson spheres, light sails, signal beacons, these aren't just science fiction tropes anymore. They're part of legitimate theoretical frameworks, discussed openly by the search for extraterrestrial intelligence, SETI, and other scientific communities. WR-140 is likely natural, its pattern is rooted in physics, and its behavior matches decades of models. But the lesson remains, the universe can produce symmetry, rhythm, and elegance on its own, which means any true alien structure would have to be even more precise, or cleverly disguised as something ordinary. This is why astronomers insist we must remain open. Not every anomaly is proof of intelligence, but not every explanation should end the conversation. The search for life among the stars depends not only on technology, but on curiosity. The willingness to look twice, to ask, what if, even after we think we know the answer. Because as WR-140 has shown us, sometimes nature creates things so perfect, they force us to question what we thought we understood. And the tools that allowed us to see it are just getting started. What this means for future astronomy. WR-140 wasn't just a fascinating object, it was a turning point. It marked the moment when the James Webb Space Telescope began fulfilling its true promise, not just to capture stunning images, but to change the way we understand the universe. With every new observation, JWST is peeling back the curtain on cosmic phenomena that once seemed too faint, too distant, or too complex to grasp. WR-140's ripples were the first of many secrets now being unearthed. Wolf-Rayet stars, in particular, are back in the spotlight. Systems once dismissed as unobservable or chaotic are now becoming models for precision and predictability. But this goes beyond stars. The ability to see through dust, measure light with exquisite accuracy, and detect the faintest of heat signatures opens doors across astrophysics. Star nurseries, black hole accretion disks, the atmospheres of exoplanets, structures at the edge of the observable universe. All of it is now in play. And as the telescope continues to survey the sky, it's likely to uncover more WR140-like systems, each with its own rhythm, structure, and story. Some may be sharper, some stranger, some older than we expect. Each one will be another puzzle piece in the grand mosaic of stellar evolution. What WR140 proves is that beauty and science are not separate. In the cosmos, they are often one and the same. And if a dying star can leave behind something this breathtaking, who knows what other wonders await just beyond the veil? Because the deeper we look, the more we realize the universe isn't just expanding, it's revealing. Are we ready for what comes next? The story of WR140 is far from over, but its impact is already echoing. It reminded the world that truth can be stranger than fiction, and that sometimes the universe itself creates images more hauntingly beautiful than any artist could imagine. We looked for aliens and found physics. We searched for structure and found rhythm. We chased mystery and found meaning. But perhaps what's most powerful is what WR140 symbolizes. It's a signpost, a celestial bookmark in humanity's journey to understand the cosmos. With each JWST image, we step further into that unknown, not blindly, but bravely, equipped with better eyes, sharper questions, and an ever-deepening sense of wonder. And while WR140 didn't prove we're not alone, it reminded us of the scale of the question, that in a universe of such intricate natural design, the line between wonder and witness is thin. Whether alien or not, every ripple in space carries information. Stories written in light, dust, and time. So are we ready for what comes next? Ready for the next strange image, the next cosmic anomaly, the next time the universe stares back through the lens and asks us the questions? Because if WR140 is any indication, the answers may not be what we expect, but they will be unforgettable.